So our next speaker is Professor Ravi Raghunathan, who will speak on the absolute convergence of automorphic Dirichlet series.
Okay, so thank you, Ram, and of course, thanks to the organizers for the opportunity. I've known Srini for a long time, but Kalyan for less time than we met a few times. But with Srinivas, I think I can remember an association of at least 22 years. So anyway, glad to be here on this occasion, and wish you both the very best in the future. Okay, so the title is, as I will shortly tell you, slightly misleading, and so let's see why that's the case. Okay, so let me state the theorem up front. This is the main theorem. Yeah. So let pi be a cuspidal automorphic representation of GLN over Q, and you take the associated standard L function, and of course I'll assume it's unitary for okay. And then the theorem is an omega result for the symmetry function of the absolute values of the coefficients. So the theorem says that summation absolute value an, n less than x, is omega of x to the half plus 1 over 2n. So in other words, the abscissa of absolute convergence must be at least 1 half plus 1 over 2n. Okay, so it's a lower bound. And of course, if I'm working over number fields, then correspondingly one has to take the degree of the number field into account, and I will get 1 half plus 1 over 2rm. Okay, so and you can see that the bound of course gets worse as the degree goes up. Okay, and to my surprise, and perhaps I will be corrected by somebody in the audience, the theorem appears to be new even for L functions of mass forms associated to higher level congruence groups. Congruence subgroups. In that case, of course, m equals 2 and r equals 1. That's not for the absolute value, that's for the summatory function. Yeah, so I'll get to that. Yeah, here, sure. So that's the difference. I'm actually looking at the absolute value of the coefficients and taking that summatory function, not just summation an, which will of course decide whether the series converges or not. Okay. All right. So let me say what was known before, and also this might explain why my title is slightly misleading. I'll explain that. So theorem 1 was known, that is this version of the, so this was theorem 1, so this half plus 1 over 2m was known for series of degree m in the extended Selberg class, and this was the work of Kaczorowski and Perelli, okay, in 2005. And here's why I believe the theorem is new. Technically, elements in S sharp are required to satisfy the analog of the generalized Ramanujan conjecture, GRC at infinity, which is equivalent to the so-called Selberg eigenvalue conjecture in the case of mass eigenforms. So, and since the Selberg eigenvalue conjecture is very far from being established, Kaczorowski and Perelli's result does not contain ours. Okay. I should also say our method of proof anyway is completely different. So we certainly recover the results of Kaczorowski and Perelli, and our proof is completely different even in that case. Okay. And we will deduce theorem 1 from a more general theorem valid for a class of Dirichlet series A sharp, which is much larger than the class S sharp. And this A sharp will contain S sharp of course, but it will also contain the L functions of all the unitary cuspidal, in fact even the globally generic automorphic L functions of GLN. So for those of you who are not familiar with automorphic forms and L functions, the case to keep in mind is say mass forms and maybe symmetric powers of the mass forms. So at least for n equals 2, 3, 4, the symmetric nth powers have all the nice properties that you want from an L function. There are other examples in higher degree, but if you want to think of a test case where the theorems are new, then mass forms are the things to think about, and L functions of mass forms is where you will get a new result. Okay. So let me just define that series. So I gave a talk in Pune a week ago where I did this. I should also say in general I like doing propaganda for this class, and I will tell you why. It generalizes the Selberg class, and as I like to emphasize, this is a class which contains all the LS pi's, where pi is cuspidal automorphic, and this is exactly the class of L functions that are of real interest in number theory, right? Whereas the Selberg extended Hilbert class a priori doesn't have. So anyway, the class consists of monomorphic functions given by Dirichlet series in some right half plane, and I will assume that the abscissa of absolute convergence is greater than or equal to half. If it's less than half, it's even less interesting because it's going to have a functional equation. Okay. There is a polynomial Ps times such that Ps times Fs extends to an entire function, and such that you have the usual finite order condition in vertical strips. So you don't want the function to grow too fast, and this condition is also saying that the function, the meromorphic function, has at most a finite number of poles in the entire complex plane. Okay. So that much is built in, but I'm not assuming it's entire, for example. I'm not assuming the pole is only at 1, which is a traditional assumption one makes in the Hilbert class. And finally, one assumes a very general form of the functional equation. So not only do I assume that you can have gamma functions of a pretty general kind, gamma lambda js plus mu j, and as many as you like, and the lambda j's can be real numbers, positive real numbers, but there's no other restriction on them. But I also allow gamma functions in the denominator. For this particular talk, allowing functions in the denominator is not that important, but all the proofs work anyway with gamma functions in the denominator, so why not? Yeah. So here it is, lambda j prime, these things that occur there, they are completely arbitrary positive real numbers, and mu j prime are completely arbitrary complex numbers. So I could have something like gamma s by 2 divided by gamma s plus 1 by 2, for example, as a factor that occurs. Okay. And what is the role of this gs? So I'm assuming that the phi s, which is this function, q to the s for some real number q greater than 0, gs fs satisfies this functional equation. Phi s equals omega times phi bar of 1 minus s bar, right? And omega is some complex number. In fact, in all examples, absolute value of omega can be taken to be 1, and so one might as well assume that. Okay, so this is what, as many of you will recognize, of course, familiar L functions like the zeta function, Ls chi, L function of a modular form or a mass form suitably normalized, all of these L functions lie in this class, but more, which is the point. So anyway, associated to each Dirichlet series, Fs, right, is a non-negative real number, so I'm taking twice the sum of the lambda j's and subtracting twice the sum of the lambda j prime, lambda prime j prime. So I have some functions in the numerator, some in the denominator. I'm taking the lambda j's from the denominator, adding them up and subtracting the lambda j's in the, lambda j's in the numerator, add them up, add up the lambda j primes in the denominator and subtract. So that is what I will call the degree of the Dirichlet series, and it's not hard to show that this does not depend on the choice. See, a priori, there could be more than one functional equation for the L function, but this number, the degree, does not depend on the choice. So it makes perfect sense to say the degree of a function f in this class is something, and I will denote the class of all functions in A sharp such that df equals d. I will denote it by A sharp d. Okay, so that's the degree of the thing, and of course, for the familiar examples, the degree of the Riemann zeta function is 1, the degree of an L function of a modular form is 2, the degree of symmetric square of a L function of a mass form is 3, and so on, right? Okay, what you expect. So the theorem we will really prove is in this class, which is why I said theorem 1 is slight, and the title is slightly misleading. So if f is in A sharp d, so I have a function of degree d in this class, and it's represented by this Dirichlet series, then for this Dirichlet series we have this omega result, the same symmetry function as we took in theorem 1. So take summation mod n less than x, and we get this omega result with x to the half plus 1 over 2d. So what I'm actually proving is a more general result, and in some sense, as I will point out, this class can't quite identify, which things inside are automorphic. So, it's more general. In that sense, it's disappointing because it doesn't single out perhaps the most important L functions, but on the other hand, it contains lots of other examples that occur in number theory. Okay. So in particular, the abscissa of absolute convergence sigma A satisfies this. So same result as before. So what I will actually do is talk about this theorem, and the other theorem, of course, is a corollary because all those L functions lie in this. Okay. So as discussed, all of these L functions, Ls pi, where pi is a cuspidal automorphic representation unitary of GLM AK, they lie in this class. And the same is true for the larger class of globally generic representations, whatever they are. So let's not get into that. But for instance, if pi is associated to a holomorphic cuspidal eigenform, or more generally is associated to a symmetric power of such a form, then LS pi is actually in the extended Selberg class S sharp, and the Sato-Tate conjecture, for example, which is known, will tell you that sigma A equals 1. You can't do better than 1, obviously, right? Because a lot of the eigenvalues will be near 1 itself. Anyway, okay, the absolute value is what we're taking, so it's going to be that. Okay. In fact, yeah. So our result is sharp. So if you look at something like zeta 2s minus half, then that will converge for real S greater than 3 by 4, and that's exactly the bound we have. Okay. So this, of course, half integral weight modular forms indeed lie in A sharp. So it encompasses that class, and we could have examples like this. They're there, there's nothing you can do about them, there's nothing you want to do about them, right? So these functions are there, and indeed they give you the sharp, so that tells you this theorem is sharp, you can't do better, okay? And just as a general remark, for instance, the L functions of Siegel modular forms, which in general are not globally generic objects, they also lie in this class. So our class A sharp does contain a lot of other L functions also of interest, and this is the best result one can prove as far as convergence goes for the absolute convergence goes. Okay, so yeah, so this is a remark I made before. Since S sharp is contained in A sharp, we recover the earlier results, but I think our proof is shorter and more elementary and applicable in a larger class. Okay, so I'm actually going to jump more or less straight into the proof. It's not a very long proof, but still perhaps too long to fit in the next 15 minutes, so I'll give you a rough idea of how the proof goes. Okay. So the proof will use a transform that was introduced by Soundararajan about 20 years ago, in 2005, and he did it for the case D equals 1. He was interested in classifying elements in the Selberg class. It's a very nice paper actually. We will use it for a general D. We have to modify that transform slightly to adapt it to our purposes. And one of the key inputs of Soundararajan is the usual stationary phase argument. But what we will be able to use is a refinement of that stationary phase argument. I used it first in a paper with Balu, and that technique is based on a lemma Bourgain-Bombieri from 2004. So I will try to explain what that lemma is and why things work out better. Yeah, it's actually all elementary. It's a very nice lemma. It's completely elementary, but it's quite powerful. Okay. So when we use all of these things, finally what we will get is an asymptotic formula for what's called the standard additive twist. So you take summation an and take e to the minus id alpha, and then you allow n to the 1 over d. So it's not a linear twist, it's a fractional twist. Okay. So you take this this particular series, you say sum it between t and 4t, and you end up getting an asymptotic t to the half plus 1 over 2d. Okay, and plus an error term which is smaller, yeah, and that error term is smaller only if I assume that sigma A satisfies this property, that sigma A in fact violates the result that I want. Okay. Sorry? That will, okay, so this is just a kind of, there will be some conditions on alpha, not a serious condition, but it's, yeah, technically it's not true for all alpha, but it's true for alpha, say large enough, whatever. Yeah, okay. So if you have this alpha, so once you have this is obviously a contradiction, because by a standard, say, tetradic decomposition, you will get the same asymptotic going all the way from 0 to 4t, and that will mean that this Dirichlet series has a pole at half plus 1 over 2d, which will contradict the fact that the abscissa of convergence is less than half plus 1 over 2d. That's right. So the point is to extract this particular asymptotic for these non-linear additive twists, as they're called. Okay, so the peculiar thing here is you have e to the minus id, but alpha n to the 1 over d. It's not n, right? Which is the standard thing that will come in character sums and things like that.
Using that last one.
Sorry?
There are 2D lists, 1 over 2.
Where?
1 over 2D.
Here?
No, last line.
There, right?
Oh, yeah, I'm sorry. That should be half plus 1 over 2d.
That's a 2D, yeah.
Yeah, sorry. The typo there, that's half plus 1 over 2d. Yeah, okay. All right. So I should say that there is independently this asymptotic formula for the standard. This formula is proved unconditionally, so to speak, with just assuming that sigma A is less than or equal to 1, I need this stronger hypothesis, right? So they have that anyway for elements in S sharp. Okay, so how does one go about doing? So let me first introduce Soundarajan's transform, and it's a very interesting thing. So I'm going to record it here, possibly for use later. They have called it K. So 1 over root alpha is obviously not that important. Kt is my notation, and I've got f half plus it. So I'm taking my series on the line half plus it, I'm hitting it with this function e to the I dt log of t by e alpha, that should be right. I don't think I have a pi there, right? And then a minus I pi by 4. Okay, so I'm looking at this thing. The point is this factor, so this is just for later possibly. The point is this factor here cancels out the growth due to that the growth of the series on the line s equals half that you get if you use Stirling's formula on the gamma functions. So when you have a degree d thing, basically it will grow like this, and this factor will cancel out that growth, so to speak. So it kind of keeps things under control, and yeah, okay. So Kt itself will be this particular interval between 2 alpha t and 3 alpha t, and of course things will be chosen suitably later. Alpha will be chosen suitably and large. Okay. So Soundarajan introduced a mild variation of this, right? And we use a similar transform to study the elements of A sharp D when between degrees 1 and 2. In fact, we showed there were none of them. There were no such elements. Okay. So what follows, alpha will be fixed basically, and we will study the behavior of H alpha t as a function of t. And I'm going to use a lemma in the next slide when z equals half. So I'm going to get an expression for f half plus it. Again, this is a totally standard lemma. So let me just also record it. So under suitable conditions, if f is in A sharp D, suppose it's holomorphic at some point S, which is z plus it. Yeah, and I have some conditions which let's not pay too much attention to them, right? The important thing is I have an expression f z plus it equals a convergence sum. So I can make 1 plus it an e to the minus n over x to the p and divided by n to the z plus it, and then I'm just going to write plus r1 plus r2, and the basic point is r1 and r2 are relatively small residue terms which can be controlled quite easily. Okay, they're not going to pose any serious obstruction to what we want to do. They're quite small. So basically this comes in the standard way, applying the Fragment-Lindelof principle, shifting the line of integration, you pick up some residual terms and you can estimate those. They won't really bother us. Okay. So as you can see, for example, r1t looks like x to the sum sigma a minus x, but then e to the minus mod t by rho. So this is a factor that's going to really decay rapidly. In fact, it's going to be 0 if f is entire, and then there's another term which also has relatively slow growth. X will be chosen suitably so that this term has relatively slow growth. But the takeaway is I can express f in terms of a convergence series plus two terms which don't affect things too much. Okay. And now let's put f half plus it in Soundarajan's transform. Okay. So there it is. I put in that Dirichlet series, and in Soundarajan's transform, what do I need to do? I need to integrate. I'm integrating on the interval 2 alpha t to 3 alpha t. I'm integrating this function. So I've now substituted a convergent Dirichlet series plus some error terms for this particular function. Okay. So we'll do that. And perhaps you can, if you don't remember the definitions, perhaps that's readable. I'm not sure from the back. Okay. So let's do that. When I put it in, I get a series after switching, of course, the integration, right? There's in here, that will be an integral. So I'll be switching the sum and the integral, and that integral is now caught inside this in. And there will be two error terms coming from the small r1 and small r2, which we will be able to take care of easily. So take my word for it, those are not the terms where anything bad is going to happen. Okay. So here is in. This is the thing I really need to look at, right? So for what it's worth, I will record it, we'll see. In equals in alpha t, capital T, that's going to be equal to, okay, 1 over 2 pi I, not so important, but, and kt, and e to the I dt log t by e alpha xn, and then here's a minus I pi by 4. So, okay. All right, so that's what it is. And xn is n to the 1 over d. So you can see that the twist n to the 1 over d is already making its appearance. Okay, it's over here. There it is. Okay. And it's easy to see that R1t is eventually going to be small. In fact, it's going to have some exponential decay term. And R2t will also be small eventually when I choose x1 suitably large. Okay, so this is, let's go to the actual interesting thing. This is the thing that where you really need to use the Bombieri-Bourgain lemma, where you gain in the stationary phase argument. Okay. So here are two lemmas. This is the standard stationary phase that, you know, I'm sure most of you are familiar with, right? If you can, so you have an integral of the form gt times e to the minus ft, and if you can bound f prime t below by something and g of t above by something, then you get a certain bound for the integral. It's more or less straightforward. I think this is familiar territory. So you get 1 over m1 times mod of capital M plus integral mod g prime t dt, right? So capital M is the bound on g, and m1 is the bound, the lower bound for f prime t. So I won't spend time on this because this is a known thing. Yeah, and yeah, there are lots of standard references, but let me show you another one. This is a more subtle one. This is the lemma of Bombieri and Bourgain, and it allows you to go up to the third derivative. So I think most of us are familiar with the standard versions which involve 1 or 2 derivatives, but this goes up to the third derivative. Okay, it's a reasonably complicated statement, so let's not dwell on it too much. The point is, if you have, well, you have the C3 functions, obviously, our functions are going to be essentially infinitely differentiable. And suppose f double prime t is not equal to 0 on k, which is your interval, f prime c is 0, which is what you're really looking at in stationary phase, right? And suppose f triple prime t is bounded by m, okay, then you get some bound. So let me point out the key thing here. So you get a main term out of this integral, which is what you would expect, right? Essentially, this is putting f equals c, and this is what the value of the function is near c. So that's just there. And because f prime is 0, the function, you know, doesn't grow too rapidly near there. So you pick that up as a main term. And the key point is you have this m by f double prime c mod square. So this m, remember, is the third derivative. It's f triple prime t. Why does this whole argument work? So I'll just give you, I'm not going to have time to tell you exactly why it works, but the point is, for us, the function that's involved in the integral is essentially f of t that we will need is essentially going to be e to the I dt log t. Forget d for the moment if you will. Sorry, it's just going to be I dt log t. And this has a very nice property that its second derivative is 1 over t roughly, and its third derivative is minus 1 over t square. So which means that the square of the second derivative is going to be 1 over t square, and the square, and m also looks like 1 over t square. So this is basically becoming O of 1. Basically that's what the argument is, right? So somehow the function that occurs in the stationary phase argument is exactly adapted to this particular lemma, because it's allowing you, it's saying, look, the third derivative and the second derivative, basically the square of the second derivative basically grow in the same way, and therefore it's O of 1, so it's not a big error. So that's what it allows you to save. The traditional thing, which I suppose you call van der Korput, sorry? Saddle point lemma will have given you 2 by 5 instead, it would have given you t to the 2 by 5, and so you're saving a whole t to the 2 by 5 power in this argument. So that's what two fields medalists will get you, I guess. So anyway, right? So this is the point. So again, let's not dwell too much. There is the main term, which is exactly what you expect. It comes out of the function, and then here it basically becomes O of 1, and this is very, very small. You know, this, remember, k is something like alpha again this is going to be O of 1, right? So f prime, so it's going to be like log t or something, so it's going to be like 1 over log t, whatever it is, it's going to be very small. Okay, so now I have about 5 minutes left, so I'm going to speed up. So this is, so I've just written out what I said already. F of t looks like this. I put in all the constants, right? And I said, look, if n is much smaller than some t to the d and or bigger than 4 times t to the d, right, then in turns out to be O of 1. That comes from the easy saddle point lemma, easy stationary phase argument, lemma 2 as we call it. But in is going to be this term, root alpha d, d to the minus half, n to the 1 over 2d, and then e to the minus id alpha n to the 1 over d. This is the term that appeared in my Dirichlet series, the one for which I want an asymptotic. Okay. So as I said, the crux of the argument was exactly that. I'll just speed through this because this is the point. So the f double prime t is d by t and f triple prime t is minus d by t square. So when you do everything right and verify what you want, the dust settles, right? What you'll end up getting exactly is this. What I said, O of m by f double prime c absolute value square is O of 1. Yeah. All of this is just, you're just keeping track of all the notation. There's nothing more than that. It really is derivative of 1 over t is minus 1 over t square. That's what we're using. Nothing more than that. Okay. So as a result, you put all this together and you add this Soundarajan's transform, which is still on the board. That looks like this particular series, an by square root n, and then you have this term which is going to decay rapidly the moment n gets larger than t to the d plus rho. And then you have this additive twist, as I called it. And then there is some error term, which came basically from the R1 and R2. Okay, nothing much is happening. Now the other key idea that Soundarajan had was, look, you can evaluate h alpha t a second way. So what you do is, you first apply the functional equation to this thing. So you can replace this by, 1 minus half minus thing. Put that in. So I'm not going to do that. It will take too much time. But this is the more elementary part of the argument. So you take that, right? Use Stirling's formula. Use the basic lemma, the one that converted my function to a convergent Dirichlet series plus the 2 error terms. You do all that and you will get this as your main term. Some constant kappa times am. So suppose am is some coefficient of the Dirichlet series which is not 0. Yeah. In fact, you can get such an asymptotic for any am, which is quite interesting, right? Of course, these terms will change, but you will get an asymptotic h alpha t equals kappa am times t to the 1 plus ia. Okay. And then you get some error term. And alpha is chosen. So here we are going to make a specific choice. Alpha is chosen so that m equals cq square alpha d, alpha to the d. So this m is the m so that am is not 0. So one is assuming there's at least one am so that am is not 0. Otherwise, there's nothing to say. And there are some constants, kappa and a, they are basically come from the gamma factors. So you can write them down all very explicitly. I didn't want to put it down here, but okay. So now you have two different expressions for h alpha t, right? One involves this series, one involves this thing, and then there are some error terms. So finally, this is exactly the kind of series you want up to some extra exponential factor which is decaying when n is large. And you get this main term of roughly t to the 1 plus ia, and you have this error term which has sigma a minus half plus epsilon in there as a power of t. Okay. And now I will replace t to the d by t. I don't want to carry that around. So if you do that, you see you get a function like this. So Cn is the an with the additive twist and with this particular normalization. So anyway, what it ends up giving you is Cn times this thing has the asymptotic t to the 1 over d roughly. So I had t before, but I've replaced t to the d by t. So the asymptotic becomes t to the 1 over d. And finally, I have this error term. Now you see if you make sigma a less than half plus 1 over 2d, this term will become 1 over 2d and you'll get what you want. So okay, it's easy to see that suppose sigma a is less than this, then this term will dominate basically. Okay, and the upshot is the absence of absolute convergence of this particular series satisfies sigma al is less than 1 over d, but the equation above says that ls has a simple pole at s equals 1 plus iad, contradiction. Okay. So that's the proof. Okay, so I was actually a little pessimistic about getting through the proof, but I wanted to give some idea of what it entailed. But finally, as I said, there is, it's a very clever lemma. I hesitate to say it's a deep idea. The deep idea maybe is getting Soundarajan's transform in. But finally, it's this very clever lemma of Bombieri and Bourgain, which enables you to save a power of t to the 2 by 5 on the standard stationary phase method. And that's what makes this work. So thank you.
Thank you for that. Are there any questions?
Sorry?
Very powerful slides. So you get two expressions, right?
Yeah. So that's what. So here, I have fudge. I mean, there is some work. My point is, you have to H alpha t has this particular form. Use the functional equation. You'll get minus, half minus it, and you'll have the gamma functions coming from Stirling's formula. Put that all in, and at some point, if you do the integral, you will just get, you will get this. It will just be integral of t to the ia. Small t to the ia dt on this interval.
Okay.
And when you integrate from capital, say, t to 2t or something like that, you're going to get roughly t to the 1 plus ia. So you literally get small t to the ia and you are integrating the dt. That's it. There's nothing more to. Yeah. I mean, one has to do it, but once you start doing it, it's not complicated at all. That's the easy part of Soundarajan's argument.
Yeah, but the optimality of the estimate, you indicated at the beginning that it's optimal because d equals 1 and then a shift of the zeta function gave you that thing. But that's sort of artificial. I mean, do you have something that arbitrary high d's that shows you can't do any better?
You mean some other example?
Yeah.
No, I mean, no. Basically, it will be shifts of such things which will do it. But I can't find any way to get rid of them. I mean, they are there.
But could they?
I mean, sorry?
No, go on.
No, in the sense that, for half integral weight modular form, this is the L function of a half integral weight modular form, right? So in that sense, it's natural. Perhaps. Yeah, I myself don't want it to be there, of course.
Could it happen, some strange reason, that for high dimensions, somehow something new happens and you get something better?
See, of course, one expects 1, right? One expects sigma A equals 1. Because that's what, if the generalized auto-tate were true.
But I don't understand your class. You allow shifts, I think.
No, I don't allow, the shifts can't be too arbitrary, but yeah, effectively, I can't eliminate shifts of this kind. But, the shifts can't be totally arbitrary. For example,
because you have the gamma factors.
No, the gamma factors have no constraints either, right? So that's why, in some sense, this is a very wide class. It contains all the known examples that we have of good, Ziegler modular forms, half integral weight modular forms, etc. On the other hand, it is perhaps too big. So, and what's worse is zeta 2s minus half has an Euler product as well. So it's not clear what I should. So one thing I could think of putting is, of course, a mean square estimate. So if I assume summation mod en square has, asymptotic of t, then probably that's good enough to eliminate all of these examples. That's what I would guess. But just with an Euler product, that's not enough. I always used to think that, this condition of theta less than half, that kind, which occurs, should be good enough to eliminate lots of things, but not quite. These shifts still survive that. Zeta 2s minus half survives it's in the Selberg. If you ignore Selberg's, the infinity components, it actually satisfies the theta less than half condition as well. It's 1/4. Theta is 1/4 in this case. So, yeah, these things are actually there. They're kind of annoying.
Or you were way to, you have a question?
Oh, you were going into it. Okay. Did anybody else have a question or comment? Yeah, no, it's interesting that we expect sigma A to be 1, right? Because of
well, for automorphic, for unitary cuspidal automorphic functions,
representations.
but not for half integral weight, for example.
No, but you half integral weight, do they belong to your class?
Sorry?
Do the half integral weight things belong to your class?
Yeah, the zeta 2s minus, it's there, and I don't see a way of getting rid of it absent some kind of mean square estimate or something like that. It has an Euler product, so it's not just that, so it's number theoretic, it has a product as well in that sense. But yeah, it looks like we really need to put in one extra thing to get down to things that satisfies the Ramanujan conjecture, conjecturally.
Yeah, good. Yeah. Okay. Any other comments or questions? In that case, let's thank the speaker again.